Oh, welcome again. This is part two of chapter 7, periodic properties. This part consists of section 7.5, electron affinity. Section 7.6, we look at the classification of elements on the periodic table as metals, metalloids, that is semi-metals, and non-metals. Or 7.8, we look at the trend, or 7.7 rather, we look at the trend of group 1A or alkali metals and group 2A alkaline metals, their reactivity and physical properties. And lastly, we will look at the trend of few selected groups on the periodic table. Just like before, I will share my screen. All right, I'll share my screen and probably show you some few examples on whiteboard. Please have a piece of paper and a pen. You will be taking or making your road known. So just like as I said, what we will look at in chapter 7 part P, electron affinity, will define what electron affinity depend on the periodic table, still explained by the effective nuclear charge we looked at in 7 part A, chapter 7 part A. 7.6 metals and non-metals, metalloids, elements whose properties goes in between those of metals and non-metals. 7.7 trends on trends for group 1A, that is alkali metals, and group 2A alkaline metals. Remember the numbering of groups using the number and a Roman numeral representative. You should also know their special names. And then trends of few selected elements. Let's look at the electron affinity. What is an electron affinity? This is one of the properties of element, and there is a trend, there is a pattern on the periodic table. Before we look at the trend, let's look at how we define electron affinity. Electron affinity is simply the energy change which accompanies the addition of electron onto a gaseous atom or ion. When an electron is added into an atom in gaseous state, energy is given off. That energy associated with that change is called electron affinity. This is exothermic. Remember, exothermic are it's given off. All right, negative called exothermic reaction. This is the reaction gives what? It gives energy. All right, negative delta H. Remember that the delta H for reaction means it's exothermic reaction, You'll see the energies for these are always given as negative. The general trend here is that, if you look at the values, the energy given off when an electron is added to an hydrogen atom, it's negative 73 in kilojoules. This is always greater than 0, which means they are positive. You cannot add group 8. We know group 8, they are inert, they do not react. Okay. Across the periodic table, this is what we can conclude on the general trend on electron affinity across the period it is generally increased. So just like in part A, all right, just like in part A, if this is the periodic table, all right, what happens as you move from left to right, as you move from left to right on the periodic table generally increases, all right, increase as you go, not much in a group. So across the periodic table, maybe to avoid confusion, we can just have that and say this is the periodic table as you go across, it increases electron affinity increases as you move from left to right on the periodic table. Group 2A, all right, S subshell is 4. This explains why we see this pattern for group 2A. Remember group 2A, we are filling the 2S sub level. And with that, it's much easier to do what? To add that. For group 5A here, right, this pattern we see here, the P sub label is half full. Explaining this pattern, sometimes it's easier. It's hard to add, but here a lot of energy is given off compared to this. You are wondering why is group 4A, group 4A gives a large amount of energy, or they have higher electron affinity compared to 5A. Is because of this feeling of P sub level, and half field will make it easier to do what? Easier to add electron, For group 8, pay attention, this is 0 greater than 0, which means they are positive. Group 8A, P sub level is full. All right, there are P6, which means they have 6 electron, and therefore their electron affinities are always greater than 0. This is a typical question on an exam or quiz of the following elements that has the most negative electron affinity. Iodine, all right, you have, if let's say this is an exam, you are given the periodic table, you look at the periodic table here, we are looking at what? We are looking at the iodine is right here. Remember the trend increases as you go across. Iodine, bromine is up here, fluorine is up here, chlorine down here, hydrogen has the most electron affinity. Decrease as you go up. Fluorine has the most, because as you go down, it's just tend to decrease. Go up. So fluorine has the most, all right? Fluorine has the most electron affinity. C is the correct answer. And remember, in exam, you will not have the color coding you have here, so be able to look at that. Now, section 7.6 looking at the elements according to, or classifying element as either metals, metalloids, or non-metals. This is something we learn or we look previously. Periodic table can be broken down into metals. You see the color coding. Non-metals, which is greenish, and the purplish are semi-metals. In the exam, you will not have this color coding, but this is what my recommendation. You need to memorize what constitute semi-metals. That is boron on this side, silicon, germanium, arsenic, tellurium, antimony, tellurium. Okay, you should be able. Some others they have polonium and astatine. Antimony, tellurium, arsenic, germanium, silicon. These what constitute semi-metal. The rest, except hydrogen on this side of the periodic table, they are non-metals. Most of the metals on the periodic table, all right, are metals. Liquid at room temperature, mercury, which is number 8, is liquid at room temperature. Bromine is liquid, brownish gas. Iodine is solid. Non-metals. Please remember how to break the periodic table as 8 are metals, non-metals. You don't need to memorize all elements which makes up metals. It's just gonna be making your life so hard. That's not how to study the elements. You just have to know what constitute. I've seen students bubbling or shading on the periodic table what constitute metals or non-metals. Nonetheless, look at the change or trend in metallic character. If I have, all right, let's see this, minimize this so that I have my whiteboard. Metallic character here, this is the periodic table. Decreases as you go from left to right on the periodic table. Metallic character decreases, but it might be increasing on this side. It increases. Gotta be careful on how you interpret the direction from which you are moving from to. Coming down here, if I'm going down this way, this one is increase. And going up there are decrease. Because some questions, all right, some questions could be tailored to from the bottom to the top of the periodic table. You see this increasing going down, but it did decrease going up. It did decrease going across the periodic table or increase going this. So the metallic character has to do with where you are moving to, So you could be given a list of elements and you are asked arrange the following according to increase in metallic character. It depends on what you are given. Or according to the following, which one has the least metallic character, the most metallic character on the periodic table. Remember, on the left side of this bold zigzag, you'll see most text, most periodic table, they have this bold zigzag staircase, which separates metals from non-metals, and you gotta know which elements constitute semi-metals. Semi-metals are these purple. They are boron, silicon, germanium, arsenic, antimony, tellurium. Okay, some have polonium and astatine, but for our case, 1, 2, 3, 4, 5, 6, please take note of that. Having said that, let's look at the learning check here. Which one of the following is a metalloid? It's obvious. If I look at here, I do have silicon. All right, this is the correct answer. Chlorine is a gas at room temperature. Lithium is a metal. Number 3, sulfur. Okay. Number 16, and indium is not that's a metal. So the correct answer here is A. You'll expect that in exam. Of the following elements below, that is the least metallic character. How will you answer this? You cannot memorize all the metals, all the non-metals on the periodic table, but you shall have this so that you answer the question and eyeball. Remember, as you move from left to right, the metallic character decreases. So moving from right to left, metallic character increase. So this one is the least. Neon, organ, oxygen. This is neon. It is A. Neon is to the extreme right. This is the least. Coming towards the left of the periodic table, more metallic compared to neon. Chlorine, metallic character increases. Fluorine, compared to that, silicon. So neon, A is the least metallic. A is the least is an element with the least metallic character. It's just by eyeballing. So if this is an exam, you have to circle the element in the multiple choice for you to come up with the correct conclusion. Most metals tend to form cations. Most metals, all right, form cations by losing their valence electron. Remember, group 1, they have 1 valence electron, and therefore they'll form positive 1. Beryllium, magnesium, those 2. Group 3, the most common cation is aluminum. Non-metals, they form anions. Anions are negatively charged. If you look at this, they are negatively charged. And tellurium, well, these are non-metals, or I mean metalloids. So noble gases, they don't react. They are inert gases. Note the physical property for hydrogen. Hydrogen can act as a metal, losing 1 valence electron to form a cation, like a metal. But when it reacts with metals, it reacts as a non-metal, such as informational hydride, sodium hydride. It will accept an electron just like a non-metal. So it has a special property. Hydrogen has a special property. It can react as a metal and it can react as a non-metal. Some texts, they have hydrogen in the middle here. It's because of this property. Some, it's not just among, and that's why it is just hanging at the top of group 1 because of the special property. Oh, well, you need to know the properties of metals, the properties of non-metals. If you know the properties of metal, then you should know the properties of non-metals. We look at the metalloids. But first, metals, all right, most elements on the periodic tables are metallic. Let's see this table right here. If you look at the color coding for metals, most, over 50% on the table are metals. That is why we say that most of the elements on the periodic table are metals. And what are their properties? They are shiny. Of course, if I give you a piece of metal and a plastic or wood, you can tell, all right? You can tell that this is a metal. It has a shiny lash. It conducts heat and electricity, right? Malleable. What is malleable? It means you can, you see this? You can hammer it into thin sheets of metals. That means malleable. Ductile, you can pull. Ductile means you can pull into thin wires. To make wires, you need to pull the metals. Most of the, except mercury, most of the metals are solid at room temperature. Most of the metals are solid at room temperature. We talked about ionization energy in part A, and metals tend to have low ionization energy to form the cations. You need less amount of energy to remove fast electron. Fast ionization energy they have. So here, once you know the properties of metals, you can just negate or the opposite of what we have here for non-metals. They are not shiny, they are dull. Non-metals are dull. Non-metals, they do not conduct electricity and heat. They are brittle. It's not brittle, opposite of malleable is brittle. They are gases at room temperature. We have solids, of course, such as iodine. We have liquids such as bromine, but most they are gases at room temperature. They are gases at room temperature. So remember that they have high ionization energy. Just to give you a few examples of non-metals, all right, where they are on the periodic table, they are right here. If you look at most non-metals, they are on top right corner on the periodic table right here, all right? Found on the right-hand side of the periodic table. My exam periodic table will not be shaded, so please remember where they are. Now, properties of nonmetals include the following. They are solid, liquid, and gas. Solid, iodine, for example, is solid at room temperature. Liquid, bromine is brownish liquid at room temperature. But most of them, they are what? They are gases at room temperature. Instead of saying malleable or ductile, they are so brittle, poor conductors of heat and electricity. Okay, I guess this is sulfur. They are brittle means when you use a hammer, this is a hammer, you strike it, it will just shatter into pieces because of the brittleness. We say they are brittle, not malleable as metal. Mostly, all right, most non-metals, they are, okay, non-metals are molecular compounds. Substance containing non-metals are molecular compounds. Takes this as oxide, okay. I guess this is one of the metals, putting in water, they react readily. Table 7.3 in the text, this is just a recapping the properties of metals and non-metals, the parallel. If you look at here, these for metals, these are non-metals. You don't see gray here, but metals have shiny, lush, ferrous color, although most have silver. They do not have any, they are dull. You can say they are dull. Solids and malleable, you have solids, but they are brittle. I'll say malleable, ductile, but they are hard sometimes. Good conductors of electricity, poor conductors of electricity. Most metal oxides are ionic solids. Most non-metal oxides are molecular compounds. Tend to form cations, tend to form anions, negatively charged particles, or oxyanions in aqueous solution. Please, you know, you can make your own notes on that. Do you think sulfur is malleable? Unless you know what malleable is, okay? Unless you know what malleable means, you won't be able to really understand what this term means. Malleable mean you can hammer, using a hammer to form thin sheets of metal. And the correct answer is no, the correct answer is C. Like other non-metal, it is brittle. So it's about understanding that sulfur is a non-metal, and properties of non-metal is that they are brittle, non-malleable. Yes, be careful when you read, you should read the whole statement. Look at this, somebody can say no and forget to say it is a gaseous in its elemental form, all right? It's not about that because it is gaseous, therefore no, it's about the malleable versus the brittle So the correct answer is C for that. C for that. Metalloids, these are semi-metals, and remember what constitute semi-metals. You have to know what they are. You have to know what they are. Semi-metals or metalloids have some characteristics of metals and some of non-metals, non-metals, okay? If I look at here, these look like silicon, all right? Several metalloids are electrical semiconductors. They are used in computer chips. So that is all what I want you to pay attention. You should be able to classify in an element as either metal, metalloid, or semi-metals, the same thing, or non-metal. You should know the properties of those three categories of element on the periodic table. What I'll recommend is memorize what constitute metalloids using the staircase zigzag bold line on the periodic table, you should be able to understand or classify an element as metalloids. Name them, know their chemical symbol. Okay, let's move on to 7.7, section 7.7, group trends. And in this case, we are saying we will only look at the special groups. We discuss about special group on when we are looking at the periodic table. An element in a group have similar properties. Remember, groups or families, they share or they have similar physical properties, similar chemical properties. Groups we'll compare is group 1A, group 2A, we call alkali, alkaline earth metals, group 2A, group 6A, oxygen groups, or sometimes we call halogen, C-H-A-L-O-G-E-N, halogen, halogen, whichever way should be able to spell, or group 6, we call oxygen. Group 5 is sometimes we call nitrogen group, even though it is here, nitrogen group, group 5A, because that's where nitrogen is. Oxygen group, group 6A, or halogen, group 7A, or halogens, group 8A, noble gases, they do not react. Why, and then we look at why hydrogen is non-metal, yet we have it on the metal territory. Alkali or group 1A or just one for IUPAC system are soft metallic solids. These look like sodium. I worked with sodium before, and it's very soft. You can just cut with a knife, but they readily react with oxygen with water vapor in the atmosphere, and they are stored in mineral oil. Typically, metals properties last conduct electricity as seen here. You see they are shiny. They are shiny. Those are group 1 metals. They have low densities and low melting point. Group 1A, these are sodium, lithium, potassium, rubidium, cesium, and look at the electron configuration. We have used shorthand where the core electrons we use group 8. Nonetheless, if you look at the SN, S1, all right, they have one valence electron. There is a pattern here. There are melting point decreases going down a group. So there is a pattern here which you need to keep in mind. Their densities increases down the group. Atomic radius increases, which makes sense. Fast ionization energy decreases because as the atom gets larger, it will be very easy to remove the electron. Therefore, fast ionization energy decreases as the atomic radius decrease. So here, you should explain why, or you should be in a position to explain why they have low ionization energy. I've used the atomic radius. And also, there is the element, or there is the ionization, or I mean the C effective, the nuclear effective charge we talked about. All right, alkali in metals, they readily react with water. And there's a pattern here. Lithium in water is react, but not that much. Sodium, not that figure. But as you go down a group, potassium is more reactive than lithium or sodium. So we expect even rubidium and cesium to be the most reactive as we go down the group. They readily react with water. There are differences for group 1. If you look at group 1, they have differences in their reaction with oxygen, lithium form oxide, oxygen form peroxide, and then potassium, rubidium, and cesium, they form superoxide. Superoxide. Those are just differences of group 1 metals when they react with oxygen. And take note of the chemical formula for the product. Having explained the trend in reactivity series, and you're given the picture here, what will you expect rubidium, which is way lower than potassium? If you look at this, rubidium, let me just minimize this. Rubidium is just right here. Rubidium is right here. We have sodium, and if you look at here, we expect to be more, all right? We expect to be more reactive. So the correct answer is B, is B. Well, that is group 1A, all right, group 1A. There is an experiment you will perform or you may have performed in Gen Chem 1 lab, and this is flame test. Flame test is used to identify what element is in a particular solution. And it turns out that different elements or atoms of different elements give characteristic flame when atoms are subjected to high heat. Electrons are excited, they gain energy, and then they go to higher energy level. And when they drop down to the ground state, from excited state to ground state, they emit light or photons of characteristic wavelength. You may see it as red, you may see it as violet. If you look at the loop here, it's just had some sample of lithium solution, cut a salt solution of lithium, salt solution of sodium, yellow orange, brick red for lithium, and this is somehow violet for potassium, right? And this one right here, they raise the characteristic color of each, and this has to do with excitation and relaxation of electron. From high energy level to lower energy level, we see different photons. Here is an example of sodium lamp. All right, this is a lamp with sodium in there. The yellow color represents this, and this has to do with electrons dropping from higher energy level, say excited electron from 3p relaxing to 3s. This one electron drop down, they emit yellow photon, all right, which we see as in this. And this happened to also applies to other group 1 metals. It also applies to group 1 metal. It's just a qualitative, flame test is a qualitative test for alkali. That's group 1, and they have different colors. And you should be able to explain that. Why? Electron on 3p or on 3s, when it is subjected to high flame, they get excited, they go to 2p, and then they drop down, they emit photon of yellow color. Now, alkali earth metals, 7.5, these are beryllium, magnesium, calcium, and strontium, right here, barium, okay. Electron configuration, all of them, they have 2 electrons in the outermost shell. The properties here is the melting point. It is decreasing down the group. Atomic density increases, you should know how their pattern changes. Of course, the radius increase because of so many shells, and keeps on increasing from row to row, row 1, row 2, row 3, row 4. They have, you know, as you go down the group, also fast ionization energy increase. So what do we know as far as alkaline earth metals? Take home message here is alkaline metals have higher densities and melting point than alkaline. So if you have to compare melting point here and melting point here, all right, look at the melting point. This is way low. compared to this, right? They have higher melting point than alkali metals. Fast ionization energy are low, but not as low as those of alkali. It's low compared to other metals, but not as alkali. They readily form positive 2 cations by losing their valence electron. Look at these 2 valence electrons, the 2s, 3s, 4s, 5s, 6s. These are valence electrons, electron in the outermost shell. If you write electron configuration, 1s2, 2s2, 2p6 all the way, for each of these elements, this will be electron in the outermost shell, electron in the highest n value. All group 2 will have 2 valence electrons, and these, when they are lost, each element will form a cation of positive 2, will form a cation of positive 2. Except for beryllium, the rest readily react with water, okay? You have seen metal, you have seen metal deposit on your pattern because they react, calcium react with metals in hot water or cation in hot water to form the deposit. So magnesium here react with steam, but the other alkaline metals do not react with that. Okay. Reactivity tends to increase as you go down a group, I guess, because the more n value get bigger, we have that we have the n value getting bigger and bigger. This is what we see in terms of electron configuration for group 6. Before that, this is what I'm saying, that reactivity tend to increase as you go down a group because of the ease at which it is to remove the valence electron. Go back here and look at the ionization energy as you go down. This will need less energy to remove an electron, which explains this reactivity, that as you go down, it's very easy to remove that electron to react with other elements to form compounds. That's what I want you to know in group 2A or alkali. Halogens or group 6A or oxygen group, all right, metallic character increases down a group. Metallic character increases down a group. All right. Oxygen, sulfur, and selenium are non-metals, but the telluride is a metalloid, and polonium is a radioactive metal. So you have to see that as you navigate the group, you will go down the you will cross the metalloid. So if you look at here, 6, non-metal, here, non-metal for oxygen, non-metal sulfur, selenium, metalloid, polonium, and then you cross over to polonium, which is a metal and it is radioactive. Oxygen is more likely to form negative 2. Polonium is most likely to form positive charge. It's a radioactive, and you'll never really get to see that. Get to know the electron configuration. The melting point increases down the group, just like the previous 2 groups, their densities also keeps on increasing. Fast ionization energy is higher than group 1 or group 2, but it's small. You have also to look at that. What are allotropes? Allotropes. Allotropes are forms of Some element exists in more than one form. We call those allotropes. They are more than element existing in more than one form. Just look here. I wanted to just give you what allotropes. Element can exist in more than one form. We call those forms allotropes. For example, ozone and oxygen gas, these are allotropes of oxygen. We have allotropes for carbon. Here is diamond, is an allotrope. It's a form of carbon. We also have graphite. The pencil, the one they have in a pencil, that's graphite. These are allotropes right here. Allotropes of carbon. Different forms. We also have allotropes these are white. We have white phosphorus. So there is black what? There is black phosphorus. Two, there is the red phosphorus. There is the red phosphorus. Okay, those are three allotropes. It's just different forms of the same element. Here are allotropes of oxygen. So in group 6, oxygen has two allotropes. So there are two allotropes for that. For group 6. For group 7, they are colored. These are group 7 halogens. If you look at the electron configuration, they have 7 valence electrons. 7 comes from 2 plus 5, 2 plus 5, 2 plus 5, highest n value. Forget about the 3D here. We are looking at the highest n value, the 4s and the 4p here. If you add those electrons in the highest n value, gives you the total number of valence electrons, or just the group number. Group 7, they have 7 valence electrons. They have 7 electrons. Here, halogens are typical non-metals. If you look at chlorine gas, it's green, diatomic. Iodine is solid at room temperature. You have seen this. Maybe you have not seen bromine. I know in intro, sometimes we work with this in supplementation, chlorine, greenish gas, and brown liquid bromine. They have highly negative electron affinity. Electron affinity, negative means it's giving away heat. When you add an electron, they have high tendency to elect electron. They give away what? Heat. Therefore, they exist in nature as anions. They react readily with metals. Last, group 8, all right, group 8 elements, we know they are inert. We call those noble gases because they do not react. In fact, when Mendeleev organized his periodic table, he didn't capture group 8. In fact, they were discovered 5 years later because Mendeleev's approach of organizing the periodic table had to do with forming the oxide, just reacting oxygen with the element. And we know group 8, they are inert, they don't react. Therefore, it was missing in Mendeleev's original periodic table. Nonetheless, if you look at the outermost shell, they are filled. 6 plus 2 is 8, 5 plus 2 is 8. They are inert. The noble gases have low ionization energy. So very large ionization energy, that means it's hard to remove an electron. Noble cars have very large ionization energy here, fast ionization energy, because of the nuclear charge. All right, the effective nuclear charge is strong because of the nuclear proton. Therefore, it's hard to remove an electron. The electron affinities are positive, cannot form stable anion. You cannot add electrons for this. Therefore, they are relatively reactive and are found as monoatomic gases. You will not see, what does that mean? You will not see argon as Ar and 2 or krypton Kr2 like that, no? Or neon like this. No, 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 they're just argon, they're just krypton, they're just neon like that, to give you illustration on how they are found in nature as monoatomic gases, Now, hydrogen occupy a special position on the periodic table. All right, they occupy special position on the periodic table because it reacts as a metal. It has one valence electron. It can lose that one valence electron to form cation H+, that is reacting like a metal. But sometimes they also react by forming hydride, means negative, losing the one valence electron or gaining one valence electron H negative, such as in sodium hydride. So it can react as a metal, it can react like a non-metal. Some others have it in the middle of the periodic table, some have it at the, above group 1. This is just typical color for group 7. And in this table, let's see here, if you look at this, we have only 2. This is because this is solid, this is liquid, this is gas. And the question here is, why are more molecules of iodine seen in molecular view relative to number of chlorine gas here? We see more here than here. Why? The reason being, this is solid and this is gas. Just to give you a hint, chlorine is gas at room temperature, whereas iodine is solid at room temperature. The point here is not really to memorize this equation, but to know the properties of group 7. Know which one is gas, which one is solid, which one is liquid. Bromine is liquid at room temperature. Iodine is solid at room temperature. Chlorine is gas at room temperature, even fluorine. So remember that. Having said that, that marks the end of chapter 7. Please continue working on end of chapter problems, so that at least you are a better place to do well in the quiz. All right, I want you to use end of chapter problems, answer the odd number problems. You have the answers at the back of the book. Also, answer or complete MyLab and mastering without looking at the text. Otherwise, if you are using the text to complete the homework assignment, then you are not really preparing yourself well for the exam, because all exams, they are closed book and they are proctored by Honor-Laguerre, you know. So please complete the homework assignment before taking the quiz. By the time you are ready for a chapter 7 exam, you will have reviewed what you missed. Other than that, thank you.